Hey guys, what's up? Hello. Well, the topic today is wave function, and why is wave function a complex valued function? Now, the wave function in the most general sense is the function that describes a wave, or we can say that it is the collection of all the possible states where one is supposed to find an electron. Now, why do we have to collect these points rather than just use the classical mechanics? This is because of the some of the assumptions of the quantum mechanics. Now, see, in classical mechanics, the objects have predefined locations, such as this. I could just use a Cartesian coordinate to locate this, okay? It will be of no big deal, right? But in case of quantum mechanics, this is not the case. You have the laws of motions for the classical objects, force equals mass times acceleration, which is the second order differential equation. Now, if you solve this equation, you get a predefined locations. But if you solve a quantum mechanics, you don't have a predefined locations, but you just have these hazes of probability where you can, you can just predict, okay, maybe here, maybe here, maybe here. You can just give them a probability, and you construct a space, okay, where one is likely to find an electron, okay. So why is there why in quantum mechanics you cannot actually have a predefined location? This is because of the assumptions of the quantum mechanics. The first assumption says that the electrons, like particles, are not actually particles, but when they are moving through space, get this, when they are moving through space, they have very greater velocity, which is of the order of like 10 to the power 6 meters per second. Say the hydrogen atom in the electron in the hydrogen atom first orbit has the velocity of c over 137, which is not precisely orbit. Orbit is the classical concept. We have orbital in quantum mechanics. Now, what you need to understand is that particles moving with that velocity will never show the particle nature, but instead they will show the wave nature. They will be spread out in the space, and they can be simply represented by the superimposition of the large number of waves, where the maxima will give the place where one is most likely to find an electron. Now, there are the implications or the assumptions of the quantum mechanics is that the Heisenberg's uncertainty principle, which is going to tell you that the position and the momentum of the particle cannot be measured precisely at the same time. More accurately you try to find the one quantity, the less accurate the other becomes. Due to this reason, this is simply trying to tell you is that 0 Kelvin is not attainable. If you actually get a 0 Kelvin, the quantum mechanics will sink. The quantum mechanics will cease to work. Okay, we need a new mechanics. Quantum mechanics is not going to work at that point. So if you have an electron, it is the intrinsic property of the electron to have that uncertainty. If someone is going to ask you about the spin of an electron, you just say that this is an intrinsic property, right? In the similar manner, it is not the default. It is not the fault of our instruments to not being able to measure its properties, but it is simply something intrinsic. Okay, you just cannot do that. This is the idea that Einstein always hated. How can some system that can be observed cannot be measured precisely? Okay. Now, what you need to understand is that one of the best way to understand the wave function is looking at a fan. Okay. Now, say that this fan right now have 4 fins, right? Say that it only has 1 fin. Okay, for the simplicity, because the Pauli's exclusion principle is going to apply to it, and there is only going to be 2 electrons, right? But here is 4. So let's just say that this is an electron, and if at rest it is a particle, right? So, but when it starts moving, look at this. How so it is at all the places at the same time, and when you stop it, you just get this. You just it's like using an operator. Like, say if I use an energy operator to a moving electron, does like this. It is just going to tell you the energy at this point. It is not going to tell you the energy at different points. Okay, it is just going to tell you energy at this point. You use a projection operator, whatever operator you want to use, you just get a value at this point. Now and this is where it gets interesting. You can perform the experiment 1,000 times, and 1,000 times you're going to get with different results, different values. This is why you need to plot all of these, which is basically the wave function or the concept of the orbitals. See how the electrons, they are at one place at a time, but when they start moving, they are at all places at the same time. This is a very interesting concept. Now, another important thing to understand is that why is wave function a complex valued function? Now, the complexity of wave function can be understood in this way. First things first, Now, if you have a water wave, if you throw a stone in the water, you can actually see the water wave. You can actually see the sound wave. You know that there is a wave. You know that there is a disturbance in the pressure of the air, okay? But you can never actually see the waves generated by the electrons. It is not possible to visualize the wave nature of the electron. You just have this this concept, okay, that is just fitting into the observations, but you cannot see the electrons or the wave nature of the electrons. This is like talking about the direct lattice and the reciprocal lattice. Why we always deal with the reciprocal lattice but not with the direct lattice. This is because you never have the direct lattice, okay? In the real world, okay, you never have the direct lattice. You can actually see these electrons or how they are, or atoms, how they are arranged. You just use the projection, or you just use the X-rays to sort of map this into a new lattice, and then you go to Fourier transform this lattice to get the direct lattice. In the similar way, you cannot actually visualize the wave nature of the electrons. You just have this intuition that yes, electrons behave like waves, and this fits into the picture. This fits into the observations that we actually calculate in our real life, and that's why we are using this. And that's what is important. This is why the wave function is a complex valued function, because you cannot actually visualize the wave nature of the particle. And if you think about it, that's what quantum mechanics is all about. Just trying to find if electron is at this point at t equals to 0 second, where is it most likely to be found at t equals to 1 second. So you just sort of assign the probabilities at different points, and then that's it. If you find the position of the electron, you have just condensed an entire quantum system into the classical system. Then you just do whatever the experiments, whatever the measurements you had to do with the particles.